now that we have these limit laws, let's try and do an example to show how we could actually use them. So here we have the limit as x approaches 5 of 2x squared minus 3x plus 4. Well, the sum rule says that I could do this as the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. On the next step, I could say by the constant multiple rule, this is the limit as x approaches 5. Oh, I'm sorry, let's go back. This is 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. Okay, so now the power rule says this is 2 times the limit as x approaches 5 of x all squared, and then I'll just keep what I have over here. Okay, and then finally, I know all these are basic limits that I have. So 2, the limit of, as x approaches 5 of x is just 5. Squared then, because of the squaring, minus 3 times the limit as x approaches 5 of x is 5, plus the limit as x approaches 5 of the constant 4 is 4. Now I just figure this out. I get 5 squared is 25, 2 times 25 is 50, minus 15 plus 4, and so in the end I get 39. Okay, so what we've done is shown how the limit laws allowed us to go from a larger, more complicated function than our basic ones all the way to the limit by using all of our limit laws and some of the basic limits that we know. Now what you might be noticing is, well, why didn't it seems like all I ended up doing was taking 5 and plugging it into this function. In other words, if I go back and just do 2x squared minus 3x plus 4 with an x of 5, then I'll get 39. And yes, you will. And what we're going to see is this is a very nice property with a lot of types of functions that we'll be able to use. Specifically, what we had here was a nice polynomial function, and so what we can actually say is, we're calling it is the direct substitution property for polynomials, and let's include rational functions as well. Again, it's important to be able to know what these terms mean, polynomial, rational, and all the other ones that we're going to get to, because we're going to have properties here and further on in calculus that have to do with what type of function. So I have to know what a polynomial is, what a rational function is. So if f is a polynomial or a rational function, and a is in the domain of f, then the limit as x approaches a of f of x is f of a. What does that really mean? It says, what we're saying is that if f is, and I'm going to say for now, well behaved, so things are going nicely at that point, at a, then just plug in a to find the limit. This is very nice, because basically what we're saying is the value of the limit in this case is the same as the value of the function at a. So we don't have to do anything more than really just calculate what the function value is there, and that will give us the limit. Well, that's really nice. Does it hold for other functions? Yes. The substitution property holds for, well, I'll name a few. Sine x, cosine x, tan x, cotan x, secant x, cosecant x, a to the x, ln x, really any log of x. So any of these functions, but the key is, as long as the point is in the domain. That's the crucial thing. We need the point of interest, that A, to be in the domain. If it is, then a simple plug-in works. Let's see some examples. You're going to see how simple this is in these cases. Determine the limits. Limit as x approaches 0 of 2x minus 1. Well, 2x minus 1 is a very simple polynomial. That means that I should just be able to plug that value in. So I should just be able to do 2 times 0 minus 1. In other words, 0 minus 1, negative 1. Right. Now, how about the limit as x approaches pi over 2 of sine x? Again, sine x is one of those functions for the substitution property, so I should just be able to plug it in. Sine pi over 2, and sine pi over 2, if you remember your unit circle, there's pi over 2, that's sine there, how much you go up is 1. Done. How about the limit as x approaches 1 of ln 3x plus e to the x? Well, it may not look pretty, but this is a perfectly nice function as far as this substitution property is concerned. I just need to plug 1 into these pieces of the function. So I get ln of 3 times 1 plus e to the 1. So I'd get ln 3 plus e, which, not a number you come across a lot, but a perfectly fine real number, ln 3 plus e. And that's the answer. So in all of these cases, finding a limit amounted to just simply plugging in to the function. Now, why this is good news is a lot of limits should be very easy. Of course, we're going to take a look at a lot of the times that this doesn't apply. But even when this doesn't apply, plugging in the value can often lead you to what you need to do, even if it doesn't work.